Hi there and welcome SREcon America's attendees. My name is Andy Grabner and today I'm going to talk about automatically detect the performance and scalability issues in distributed architectures. That's a long title, I know, but stay with me. I think I have a couple of things to say about this because I've done this over the last couple of years. I not only want to show you how you can detect it, but also how you can integrate the detection into your delivery pipeline using an open source project called Keptn. So just a couple of words on myself. My name is Andy Grabner. I always say at day I work as a DevOps activist at Dynatrace. At night, I am a DevRel for the CNCF open source project Keptn. You can find all the information you need if you want to follow up later on, either with me directly or on the open source project on the links here on this page. But let's get started. Distributed architectures. So how do distributed systems actually look like? Well, maybe how they shouldn't look like in case you are challenged with the distributed systems. So let me give you an example. What you see here is a distributed trace from StepStone, a European company. I co-presented with them at AWS Summit in Berlin last year. And what you see here is basically an end-to-end distributed trace that starts on the front with front-end load balancer, and it's an Apache server. Then it goes through different legacy systems, microservices, databases, AWS ELBs, and third parties, and there's many more components. But as you can see here, this is a distributed system with a single request coming in the front, or let's say requests coming in to the front of your system, and then they're kind of spreading out across all sorts of services and components. The system obviously, like in this case, started smaller years and years back, and then over the years it grew. This company, just as many others, have started to maybe not break the monolith, but add new services around it so that they can add more use cases to it, all behind the front-end load balancer that is then distributing the load. Also adding in third-party solutions, also adding in services from their cloud vendor. In this case, it's AWS. But this is what a distributed system can look like if you're doing distributed tracing. So you see how a request is going through all the different layers of your architecture. Quite complex, you may think, right? Well, let's give you a little more ideas here. This is also a view on the dependencies. In this case, it's 323 Kubernetes nodes of one of the organizations I worked with. What you basically see here, we call this Smartscape. Smartscape shows the dependencies between nodes, between hosts, based on the network connectivities, right? And you can see nicely the clusters on the individual nodes, what actually belongs together and what doesn't belong together. Now, if we go the next step, and if we go a step higher, if you look at the processes, it's actually, it looks almost like art, but this visualizes how individual processes that run within the containers are connected with each other. And as you can see, there's a lot of interdependencies. There's also a lot of islands, I would say, right? You can see how individual pods are kind of really running maybe on a server or on a Kubernetes cluster, and they're not connected with each other. But underneath those, there's a lot of interconnectivity, and some also reach out to some of the other clusters. So having intercluster dependencies, which may or may not be intended. Overall, I think the lessons learned over the years, as you're moving to a more distributed architecture, right? The more distributed you get, the more you're breaking up the monolith, or the more you're adding services, more dependencies you will end up having. There's also on the bottom, you can see a couple of links here to blog posts that I can encourage you to read up. So behind all of my stories, there's typically a blog post or another presentation I gave. Now, obviously, it's clear that we have more dependencies, right? If you're breaking up system into smaller pieces, or if we're adding services, we will end up having more dependencies. But what's important to understand is that the more dependencies we have, the impact of a failing component within that dependency graph may grow, right? So what you see here is a classical problem ticket of a detected problem, where the problem itself was triggered by a bad update to a backend service. And then because of all of its dependencies, it is impacting not only the service itself and maybe the SLOs, the service level objectives of this service, but everyone that is depending on the service, especially if these services are not resilient enough against a failure of one component. And I think that's also very important, the resiliency, right? We are here at SRE, we talk about resiliency and reliability. So we need to understand that every puzzle or every piece of the puzzle, every service within a distributed architecture that have strange behavior because of maybe a bad update or a bug or whatever it is, it has impacts. And I think it's very important to understand in the distributed architecture who is depending on me and what is the risk of change. I think this is something we all need to understand. And again, screenshots here is what we call it the backtrace at Dynatrace, but whatever distributed tracing technology you use, it is basically the reverse distributed trace, or it's the reverse view of a lot of distributed traces. In this case, I'm looking at 5,600 requests that are coming in on the journey service, and I basically see where do these requests originate from. So that's always good to know. So with distributed tracing, we actually have a lot of wealth of information. We just need to look at the data in different ways so we can answer these very important questions. Who is depending on me and what is the risk of change? All right, so hopefully a little insight in what are distributed systems, how do they look like, the importance of having distributed tracing available because we can understand these systems much better. All right, let's go into the next phase of my presentation, common distributed architectural patterns. I've seen a lot of patterns because I've tried to help a lot of organizations over the years to understand what's happening in the architectures right now and where potential bottlenecks are. Now, there's many patterns out there. I want to focus on only a couple today. Not all of them, the list is here, only those that are in bold letters. But if you want to know more, I have given presentations like this in the past. And there's links on the bottom to some of the recent meetups and conference presentations I did, like at Confitura or at the San Francisco Java meetup. But I want to, at least highlight a couple that are very dear to my heart because I see them all constantly. Right? The N+1 call pattern problem, or better, 1 plus N, where the 1 is basically the initial call to a service, and then a list of results come back. Let's say N results come back, and then you typically have N calls to get more details about that result. It's a very common pattern. So let me give you an example. Monolithic code, right? If we have this particular piece of code where in the loop we are iterating through an array of products, and then we call product get quote, it's all in memory. It's perfect, right? I mean, it's very fast and very easy to do. But the thing is, if we extract this into a separate service, if the get quote or whatever stands behind the product object gets externalized into its separate service, which is a very common thing to do, right? Then we will potentially run into an issue. And this actually happened with one of the organizations I worked with. So quote service in the front, and then the product services in the middle, different service instances. So it was a scalable architecture. So they basically ripped apart the system, microservice on the front, and then scaled microservices in the middle, which meant that a single call that you saw earlier that came in, and there was then calculating the total sum of the products in the quote, where obviously, instead of doing these calls in the same process, maybe even on the same thread, now these calls go across network, across pods, across clusters, across networks, across continents potentially, right? And so you end up with a lot of calls between the systems. And if you don't design your interfaces correctly, if you don't provide a bulk operation here, like give me the sum of all these products, then you end up with a lot of traffic going back and forth. And this is the classical N+1 problem. To give another example, LANDBAY, another organization we worked with, and there's another case study out there, similar thing, looking at the distributed trace again. So they had an initial call coming in the front, then the call was kind of split up in putting 74 entries in a database, 24 in a queue that are then picked up by RabbitMQ listeners. As you can see here, these messages were picked up and then kind of processed in an asynchronous fashion, and then kind of forwarded to all the different services in the back that were handling these. Now, this is just the subtotal of the complete trace. This is not the whole trace. The whole trace was going on and on. But you can see that while this might be intended, but in a lot of cases, it's often not intended, or people don't think about the impact when they're designing distributed system and then having event-driven systems that are then spreading these events across many different services. And then you have a lot of components being involved and a lot of calls that might not be intentional or that could be optimized, right, through bulk operations, for instance. Now, this was the N+1 call pattern. Now, the N+1 query pattern, very similar. This is just why I separate them, because this is more focused on database queries, and I see this as a big issue. So coming back to my example from before, the quote service, the product service, same example, 1 call in the front, 87 calls to the product DB. Why? Because every time the product service was called, they had to get some initial state out of the database and then making another call to the database to actually get the data. So this was a basically a duplication. Every time you call the product service, every service had to first fetch some initial state and then execute the actual database query. So this is why this kind of ended up with 87 calls in total to fulfill a simple query that was summing up the quotes of all the products in a shopping cart, basically. All right. Another example. In this case, again, Java frontend and distributed trace of the classical N+1 query problem. So you can see here, and I'm just highlighting here, and I think you can do the math. So a single search, this was a search feature opening up or getting details about an account, going out to the database and getting history of that account. And it was basically ending up with calling 26,000 database calls to the Postgres database in the backend. This is by far, obviously, very visible. It's not efficient, right? I mean, there's definitely better ways. When we see these things, we need to figure out, is there a better, more efficient way to solve this problem? Another pattern is what I call payload flood, or also known as sending useless information across the network. Here is an example of an application that was receiving an initial document that then was sent to a processor, a transformer, a signer, and then shipped the document back. So the process here was an electronic document that then got individual pieces of the document signed, and then kind of the whole document was sent back in its digitally signed version. And the challenge with this was that the data kind of that was sent back and forth. So the initial document was only 10 megabytes big, but then the whole document was kind of forwarded to each individual services that then added more additional data to the document. So there's a lot of data that is basically being sent across the network, because always the whole document was sent, even though the whole document was not always needed by every individual service. So in the end, they were looking at this and they were then changing the architecture so that only the relevant pieces of the document were actually then sent to the individual components until the final document then was sent to the doc shipment that kind of put it back together. But you can see here, this is reducing the network overhead by more than half, which is a lot if you think about how many documents might be sent for digital signature. Therefore, sending a lot of network bandwidth, a lot of CPU for analyzing and parsing the docs all the time. So these are the things that we need to look out for. Another thing, inefficient service flows. This is where I'm drawing parallels to web performance optimization. So about 8-9 years ago, I was very involved in web performance optimization, so in analyzing speed of web pages when they load. And we always looked at waterfalls. I'm not sure if you've ever, in your browser, if you open up the browser developer tools and you hit mostly F11 or F12, and then you see how the page is loading. So you will see something very similar in a couple of seconds. Remember this year, distributed trace. Again, this is what we, in Dynatrace, we call it a service flow visualization, how transactions flow through the system. And this is just a single application, request coming in to the varnish cache, and then if it's not in the cache, it goes on. Now, over the years, not over the years, over a couple of sprints, we have extended this application, and the distributed trace ended up like this, because more services were added. We made classical problems of not adding enough caching layer. The N+1 query problem was introduced of one service calling the other multiple times for every individual result without thinking about the bulk operation. And this is obviously something we need to have in check. We constantly need to look at these traces and see how are individual code and configuration changes and architectural changes impacting my end-to-end distributed architecture. Another interesting thing from another application is this cascading effect. And this reminded me kind of the waterfall graphs we looked at when we analyzed slow web pages when they were loading. You can see here how always the application was like calling the same bulk of services over and over and over again. And this was, I think this was a search result, so a search page, and then it was reaching out to a backend service and then getting more details about this particular batch of results, and then the next one. It's cascading and a lot of recursive calls. So not pretty, right? I mean, maybe pretty if you like the waterfalls, but not pretty when it comes to distributed architectures and efficiency. So let me quickly recap on what we have seen so far. And I know there is definitely much more we could go through, but the top ones that I constantly see have been covered: the N+1 call, the N+1 query, the payload. There's other things in there, but the main point here is that, yeah, I mean, I've showed you visualizations of distributed traces and so on, but in general, we can detect these patterns by looking at a couple of metrics. Let's say the N+1 query problem, right? If you can count the number of SQL invocations or the number of same SQL invocations, then you can easily say, hey, at the end of my transaction, how often did I call this database statement? Oh, I called this once and then this 5,000 times. That's interesting. That's a clear indicator if the same statement is called multiple times all over, that there's an issue. Also, transfer size. If you are sending a lot of data over the wire, monitor this. And you can look at log files, or you write your own metrics to your metric store, or you're using a monitoring solution. Then you get a lot of metrics that can actually tell you, by looking at these metrics, if your system, your architecture is suffering from these common distributed patterns. Reminder, if you want to see a more detailed presentation on all these patterns and the metrics, check out these two recordings, and there's also some blogs out there from me. Just Google maybe for top performance problems and my name, and then you'll find a couple. And there's also other people that have obviously talked and blogged about this. Now, the next question is, can we automate pattern detection, right? And if so, right, how will we automate that? So first of all, as I just told you, yes, we can automate it, or we can use metrics for it. And typically, I start building a dashboard that shows me exactly these metrics: how many database calls, how many backend service calls, how much data is transferred. And this is great, but then the question is, well, how can we really automate that? Because I don't want to look at the dashboard anymore. Because really, what I don't want is, after every code change and after every build, that I have to open up that same dashboard in whatever tool that is, and then manually have to say, okay, yes, it looks good again. Yes, it looks good. Oh, now we have a problem. So in order to automate that, I want to introduce you now to Keptn. Keptn is an open source project that has automated exactly this particular process of looking at metrics for you, comparing them either against an objective that you have. So for instance, you're not expecting more than 5 database calls for a particular transaction. If there's more than 5, then there's a problem. Or it can also compare it to previous metrics from previous runs, so you can easily detect regressions. And Keptn automates all of that, and we are introducing, or we're using SLIs and SLOs, service level indicators and service level objectives, as the core concept on how you define which metrics and the objectives. And because it's fully automated, and Keptn provides also an API to trigger this and to get the results through an API, you can easily integrate this in your testing, delivery, and also auto remediation. So let me quickly introduce you to Keptn. As you can see here on the links on the bottom, Keptn.sh is the website. We find us on GitHub, also on Keptn. What Keptn really is, it's a declarative, extensible automation of SLO-driven delivery, quality gates, and remediation. Now, I know, again, this is a mouthful of a lot of buzzwords maybe, but let me show you what Keptn, the architecture, looks like from 10,000 feet. You install Keptn. Keptn is a container-based event-driven system, so you need to install it on any type of Kubernetes flavor. You get a control plane that manages processes, and it uses eventing to then connect the process with the actual tooling. That means, as a first step, you actually go in and define the processes that you want Keptn to execute. We support two major processes. One is around delivery. This is where the shipyard file comes in, where you specify in a simple YAML file which stages you have and what should happen in a stage. And then the second use case is remediation, or automating operational processes. Remediation around, if there's a problem coming in, which actions should be executed. So you define the process. On the other end, you define what's tooling, and because it's an event-driven system, you basically just say, I have these tools that are listening to these types of events that Keptn sends in order to enforce the process. Which means, if we take one of these processes, the delivery process, a developer can say, I have a new artifact, and Keptn, you already know the delivery process that was defined by the site reliability engineers, and you know which tools to use, because the DevOps team, they have enabled the tool integrations that are now listening to these events. Then Keptn is basically taking this artifact and executing the workflow by sending events, and then the individual tools are taking care of it. All right, so that's kind of like a quick overview of Keptn and the architecture. So what you need to take with you is declarative workflows, and everything is event triggered. That means the events itself trigger then actions and tools, or triggering basically tools that can do certain things. All right, so let's give you the first use case. Coming back to the presentation, automated architecture and performance validation. The thing what we could do, and what a lot of organizations have tried to do, is, right, if you are using some automation where you build and then deploy and then run some tests against the system that you've just built, that's great. But then typically there's this manual time, this lengthy time, where then somebody needs to look exactly at the data I showed you earlier. So we need to look at the distributed traces and figure out, is there a difference from one build to another. We may need to look at metrics, right? The stuff that I've showed you earlier. Yes, it's all possible. We can look at this, but this is very cumbersome and it takes a lot of time. And this is where I want to propose the automated way that Keptn allows us to do. And this was actually inspired by something one of my colleagues has done at Dynatrace. He's been doing this for a couple of years. They are deploying a new version of the app on a regular basis, like daily, into an environment that is constantly under load. And basically what they are calculating while the test is running, they're looking at key metrics and they calculate what they call a performance signature, right? We are a performance company, so that's why we call it a performance signature. But essentially, it's very easy. What they've built is after every deployment, after the test is running for a while, they were then pulling data out of the testing tool, out of the monitoring tool, and doing this for every build and pulling out multiple metrics and then simply comparing these metrics either against some thresholds that they had in mind that they knew they should not cross, or against the previous builds, and therefore they came up then with a very easy red and green heat map. Right? It's something very simple. And if you want to know more about this, there's also a link to a presentation that Thomas Steinmauer actually did at NEOTIS conference. So what does this mean? We took the same concept and put it into our Keptn open source project. So one of the things that Keptn can do in orchestrating a process is a so-called quality gate enforcement. And we're using SLIs and SLOs for this. So what this means, Keptn is event-driven. That means you can integrate any type of monitoring or any type of testing or any type of metric data source into Keptn by simply hooking up your tool with the eventing framework of Keptn and then listening to the request when Keptn needs metric data. Now the question is, how do you tell Keptn or that tool what type of data you want? You specify so-called SLIs. So you specify your SLIs in a YAML file, a metric name like error rate, and then the query language or whatever they identifies in that monitoring tool or data source. So you specify your indicators, your metrics, and then you specify your SLOs. SLOs basically are, what are your objectives for a particular metric that you consider then good or no good? And once you have set this up, then you can say, Keptn, please you now send events to these tools, tell them what type of data we want based on the SLI YAML, and then we compare it against the objectives. So Keptn sends out the events, the individual tools return the data. Once the data is returned, Keptn compares it against the SLO definition, is then grading every single metric. If it's green, yellow, or red, gives it points, and then overall calculates a total score, which we then normalize to a value between 0 and 100. So we can easily say how many points did you achieve. And I think that's actually hopefully pretty straightforward, which means when we integrate this into the delivery process that I showed you earlier, and when you are running your tests and then using basically Keptn to automate what you would normally do, meaning looking at the data, looking at the dashboards, but instead of you looking at it, you say, you do this for me. You pull out these metrics and you compare them to these metrics against these objectives, and then you return a score. And then you can reuse this score to then report it back to your pipeline, whether it's Jenkins or any other tool. And this reduces, obviously, that time dramatically. So a quick demo. Now this works, as I said, with many data sources. We have an integration with Prometheus, with Neotis. People are currently working on a Splunk integration and a Wavefront integration. I'm using the Dynatrace integration. That's my monitoring tool of choice because that's the company also I'm working for. And the way we actually did it there, you can still create your SLI and SLO YAMLs, but we made it even a step easier. The only thing you need to do in our integration, you just build a dashboard, and this is then the dashboard that will be transferred into the SLI and SLO YAML with all the information that is on there on every metric, and then Keptn will automate the analysis. Okay, so let me quickly show you. So here is my my Keptn front end. Let me just quickly run a pipeline. I'm using Jenkins here. I can say build with parameters, and I just say Keptn. Keptn is organized in projects, stages, and services. And here I can specify a time frame. So I just run that build. So now Jenkins makes an API call to Keptn and say, Keptn, you know all the configuration already. I told you what I'm interested in, but now you do it for a particular time frame. And as you can see here, it should probably take about 11, 12 seconds. And then the result should be here. This is job number 112. And once this is done, we should be able to get the result. Let's see, my Jenkins is a little slower today than yesterday, but still, I think we are going to get there. All right, so while this is running, let's give it a couple more seconds, then we should be good. The great thing is you can integrate this with any type of tooling. We have an API. We also have a CLI for that. So now it came back and it says unstable. So if we look at this now and we see Keptn results in Bridge, we can open up the direct link, and now we can see, okay, what actually happened. So on the right side, this is now the process. So I'm not using the whole end-to-end delivery process that I showed you earlier. I'm just specified a small process that is basically just an evaluation. So evaluation started, retrieved. And then here I can see all the individual metrics. So every row here is a metric on SLI, and then we get to see the actual value and the overall score. I see the individual values, obviously. I can also go back and I can see some of these metrics over time, right? In case I want to know how certain metrics have evolved. I can obviously look at the SLO underneath, or in my case, I can just open up that dashboard, because really the configuration about what I want Keptn to analyze is just all in this dashboard for me. And then Keptn is just automating that. And this again works for Dynatrace, for Prometheus, for any other type of system. All right, so let me go back because I have about 8 minutes left. User examples, right? It's not just me giving you the demo. We have examples of customers or users that are using this. Christian is using GitLab for build, deploy, and test, and then they really just integrate Keptn to evaluate how individual metrics are doing, whether this is performance metrics, regression, architectural metrics like number of database calls, bytes sent over the wire. All of these metrics can be fully automatically analyzed. And I think this is the great thing, because you can, if you integrate this with your CI/CD, you immediately get feedback if any of the code changes has introduced an architectural, a scalability, or a performance regression based on the metrics that you know are important for your architecture, because you've done your analysis on problem patterns maybe before. Second use case, and I thought this is also very interesting, especially now for SREs. So remember, first use case was automating the evaluation of metrics to detect problem patterns and performance problems and architectural problems. Second use case is auto remediation, which I think is also very cool. I told you in Keptn, we also provide a workflow for automating, for handling problems through auto remediation workflows. So what that means is, if you have Keptn installed and if you have a monitoring tool that alerts you on a problem, like in this case, conversion rate dropped because of CPU pressure, then Keptn can orchestrate the execution of a remediation process. And in this case, you can see here, conversion rate dropped, there's 2 actions specified. So what Keptn will do, if it finds that process definition, it will execute the first action. And executing means it sends an event. So any type of action that you want to plug in can then be executed, like scaling up. Then the important piece is, it's not a fire and forget, but it is going back to the same SLO quality gate example that I showed you earlier. It is evaluating if the system is back to its desired state based on important SLOs that you have. We also call them BLOs here, business level objectives, because if this happens in production, then you may also include things like user experience, conversion rates, and all that stuff. And if for whatever reason that action does not bring the system back to a healthy state, then Keptn can trigger the next action and then evaluate again, hoping that everything go back to normal. And if not, then obviously we can still escalate. So this is obviously looks great, sounds cool, everybody wants to do it, but a lot of people are very scared of doing this the first time in production, because basically you're executing code, which is the remediation code, in production the first time. And I think, like we do test-driven development, we should also do test-driven operations, which means we should test the stuff first. And I think chaos engineering is actually perfect for this, because in a pre-prod environment, you can enforce chaos on your system. With this, you first of all validate if your monitoring works correctly and if your alerting works correctly. And then you can strengthen and test and validate and optimize your remediation workflows to make sure that your system that you're setting up can actually bring your system that is currently experiencing a chaotic situation, it can bring it back to a healthy state. And this is just the same example as I showed you earlier: executing action, reevaluating, execute the next action, reevaluating, and hopefully everything is good, or escalate. But this is a great way to really test drive your operational code, which in this case is auto remediation code that get executed in case there's a problem. All right, good. So then let me wrap this up. What you should have learned today is this. The first thing and most important thing is, you need to look at your applications. You need to understand the patterns that you currently have, that you may historically have, or that are common patterns in the architectural choices you have made. There's a lot of material out there, as I said, but I think it's great to start by analyzing what makes up your architecture and what can potentially go wrong. Also look at things like when you had problems, do a post-mortem on production problems maybe, or a post-mortem on when you detected performance or scalability issues. Understand your patterns, and then actually not drive, but I should say derive the metrics. So based on those patterns, say which metrics can we look at to detect them easily, because looking at pictures is one thing, but if we have metrics, then it's easier. The next thing is, look at these metrics and then put them on a dashboard. Put them on a dashboard so that you make it easier for you to analyze this, and then also then start thinking about what are expected thresholds, what are your SLOs, your objectives. So what are your metrics, SLIs, and what are your objectives? So that you always know if this threshold crosses a certain, if this metric, if this SLI crosses a certain threshold, then I'm alerted. And then if we have this, then, let Keptn automate the analysis, because while it's great to look at dashboards all the time, but this is just boring at some point. That's why you can say, Keptn, you look at the metrics for me, you do the comparison, and then you tell me whether the latest build is good or no good. And if you have this, then you integrate this in your delivery and operations process. Just as I mentioned, it's very easy then to do the final step, which means automatically analyzing these metrics that are potentially highlighting architectural problems that you've just introduced through a latest code or configuration change. All right, with this, I want to say thank you so much for SREcon to host me. Hopefully this was insightful. Automatically detect the performance and scalability issues in distributed architectures. My name is Andy Grabner. Feel free to ping me on LinkedIn. Feel free to hook up on Twitter. And it would be a pleasure if you could have a look at Keptn, give us feedback. We are an open source project. We are a CNCF, a Cloud Native Computing Foundation sandbox project. We need your support. Join us on the Slack channel. Look at our GitHub repo. Extend Keptn, very easy to do. And follow us on also on Twitter if you happen to be on Twitter. All right. So with that, stay safe, and hopefully you will never be haunted again by performance or scalability issues in distributed architectures, because you're now automatically detecting them in the way I explain it to you. Thank you. Bye-bye.